Activity has shown that a radioactive nucleus disintegrates or decays spontaneously. During a radioactive decay process, the original nucleus is referred to as parent nucleus, and the residual or resultant nucleus is referred to as the daughter nucleus. In nature, a radioactive nucleus can decay by three modes, namely alpha decay, beta decay, and gamma decay. Let us first study alpha decay. An alpha particle is a helium nucleus containing 2 protons and 2 neutrons. That is, its mass number is 4 and atomic number is 2. Since an alpha particle is a helium nucleus, when an unstable nucleus emits an alpha particle, its neutron number as well as proton number reduce by 2. Therefore, when a nucleus decays by emission of an alpha particle, the mass number A of the daughter nucleus reduces by 4 and the atomic number Z reduces by 2. Since the proton number Z of the nucleus changes in this decay process, the chemical symbol of the daughter nucleus is different from that of the parent nucleus. If a radioactive nucleus X having an atomic number Z and mass number A emits an alpha particle, then it transforms into a nucleus Y with atomic number Z-2 and mass number A-4. Let this be equation 1. The heavy nucleus emits an alpha particle, thereby reduces its mass and hence moves towards stability. Alpha decay occurs in all nuclei with mass number A greater than 210. For example, americium-241 undergoes alpha decay to form neptunium-237. Americium-241 with atomic number 95 emits an alpha particle and decays to neptunium-237 with atomic number 93. The total mass of the decay products, that is neptunium-237 and helium-4, is less than that of the parent nucleus, americium-241. Hence, the total mass energy of the decay products is less than the mass energy of the original nuclide. Therefore, alpha decay is a spontaneous decay without the need of any external source. The difference between the rest mass energy of the initial constituents and that of the final products is called the Q value of the reaction. If Ui denotes the rest mass energy of the initial constituents and UF denotes the rest mass energy of the final products, then the Q value for the reaction will be equal to Ui minus UF. Let this be equation 2. This definition of the Q value is valid not only for alpha decay, but in general to all nuclear processes. Q denotes the energy made available as kinetic energy of the products. Thus, the Q value of an alpha decay can be expressed as Q is equal to mx minus my minus mhe into c square. Here, mx is the mass of parent nucleus, my is the mass of daughter nucleus, and mhe is the mass of a helium nucleus, and c is the velocity of light. Let this be equation 3. Thus, the disintegration energy, Q, is shared by the daughter nucleus and the helium nucleus in the form of kinetic energy. Alpha decay obeys both the laws of radioactive decay, that is, N is equal to N naught into e power minus lambda T and R is equal to R naught into e power minus lambda T, where lambda is the decay constant. Now let us study beta decay. In beta decay, a nucleus decays spontaneously by the emission of an electron or a positron. In a beta decay process, a neutron converts into a proton or a proton converts into a neutron. If N denotes the neutron number of the nucleus and Z is the proton number, then N by Z is altered in a beta decay process. If the nucleus is formed with more number of neutrons than the number needed for stability, then a neutron will convert itself into a proton. If a nucleus is formed with more number of protons than needed for stability, then a proton will convert itself into a neutron. Such transformations take place because of weak forces within the proton or the neutron. The decay in which an electron is emitted is called beta minus decay. In this decay, a neutral, massless particle called an antineutrino, denoted by the symbol nu bar, is also emitted. For example, when carbon-14 decays into nitrogen-14, it emits an electron and an antineutrino, which is denoted by nu bar. This is called beta minus decay since the particle emitted is the electron. Here, we see that a neutron converts into a proton and in the process emits an electron. In beta minus decay, the atomic number of the daughter nucleus is 1 more than the atomic number of the parent nucleus, with their mass numbers being the same. In beta minus decay, a neutron transforms into a proton within the nucleus. Along with this transformation, an electron and an antineutrino are also emitted. Let us now calculate the Q value for the beta minus decay. The rest mass energy of the initial constituents is equal to Ui, given by equation 4. The rest mass energy of the final products is equal to UF, given by equation 5. Then, the Q value of the reaction will be Ui minus UF. The Q value can be obtained by substituting the values of Ui and UF. Let this be equation 6. Because of the large mass, the daughter nucleus formed does not share an appreciable part of the kinetic energy. Thus, the energy Q is shared by the antineutrino and the beta particle. Now let us study beta plus decay. The decay in which a positron is emitted is called beta plus decay. In this decay, a neutral, massless particle called a neutrino is also emitted. A neutrino is denoted by nu. For example, when carbon-10 decays into boron-10, it emits a positron and a neutrino. This is called beta plus decay since the particle emitted is the positron. In a beta plus decay, the atomic number of the daughter nucleus is 1 less than the atomic number of the parent nucleus, with their mass numbers being the same. In beta plus decay, a proton transforms into a neutron inside the nucleus. Along with this transformation, a positron and a neutrino are also emitted. Let us now calculate the Q value for beta plus decay. The rest mass energy of the initial constituents is equal to Ui, given by equation 7. The rest mass energy of the final products is equal to UF, given by equation 8. Then, the Q value of the reaction will be Ui minus UF, as given by equation 9. We observe that in a beta decay process, when one nucleon transforms into another nucleon, there is no change in the mass number. Beta decay also follows the two laws of radioactive decay. Here, it is important to note that neutrinos interact very weakly with matter. Neutrinos can even pass through the earth without being absorbed and hence are very difficult to detect. Now, let us study gamma decay. In gamma decay, high-energy photons are emitted. Here, there is only a change in energy of the nucleus, but no change in its composition. Usually, an alpha decay or beta decay leaves the daughter nucleus in an excited state. The daughter nucleus reaches the ground state by a single transition or sometimes by successive transitions, emitting one or more gamma rays, that is, by gamma decay. For example, a cobalt-60 nucleus transforms into nickel-60 by beta- decay. This nickel-60 nucleus is an excited state and comes to its ground state by successive emission of 1.17 MeV and 1.33 MeV gamma rays. To summarize, an unstable nucleus undergoes radioactive decay to attain stability. In alpha decay process, a radioactive nucleus emits an alpha particle, which is a helium nucleus. Here, the mass number A and atomic number Z are altered. In beta decay process, a radioactive nucleus emits a beta particle, which is an electron or a positron. Here, the atomic number Z is altered. In gamma decay process, a nucleus in an excited state emits a high-energy photon to reach a lower energy state. Here, only the energy levels change and there is no change in either the mass number A